Today we will look at analysis, we will continue with the analysis of 1D NMR spectrum. In the last class we saw that given a structure of the molecule, how do we interpret the spectrum. Today we will see that we will not have the structure to start with, we will have only the formula. We only know the contents of carbon, how many carbons, how many hydrogens and so on. So, we will have to then when we will then be given an NMR spectrum. So, now then our task will be to find out the structure which is compatible with the formula as well as compatible with the spectrum, and we will be only using the proton NMR spectrum as our starting point. We will not have any other data with us. Typically when organic chemists analyze NMR data or for a new molecule, they will also have the IR spectrum, the mass spectrum as well as some idea of the structure, but let us see how we can analyze the data without knowing the structure at all. So, these are the 10 compounds which we will go through one by one, because this will reveal different intricacies, different types of data possible, and all of these examples have been taken from this book called Introduction to Spectroscopy by Pavia, where actual spectrum actually has been shown, but we are not going to see actual spectra here. We will only look at the typically the schematic drawing of the spectra. So, let us start with the first compound. So, this is the spectrum given to us. So, we know in this case this is the formula, this is what is the molecule which has been obtained by some other means, it could be through elemental analysis and so on. So, now this is the spectrum given to us and now we want to figure out what is the structure which will be compatible with this formula as well as with the spectrum. So, as we discussed in the last class, the first thing you will have to see is the number of hydrogens. So, if you see here there are 4 peaks, main peaks. Of course, remember the small peaks are the multiplet of J values because of J coupling, that is the whole structure together is considered as one peak. So, here is one peak, 1, 3 and 4 peaks. So, there are 4 peaks in this molecule, which immediately tells us that there are 4 different types of hydrogens which you would expect in this molecule. And the next thing is to look at the J coupling. You can see in the J coupling we are having a triplet here. This is basically a sextet, that is there are 6 peaks and this is a singlet and this is a triplet again. So, and if you count the number of hydrogen, this is the integral. So, if you see the integration is relative integration is shown here. So, see you can see there is 2 plus 3 5 plus 2 7 plus 3 10, which 10 is exactly the number which is here. So, everything is matching well, that we have the number of protons which we have corresponds to the number of proton in the molecule and also the number of types of hydrogen is now 4. So, the next task is to figure out what molecular structure will fit this particular spectrum. So, we are doing the reverse approach, that given a spectrum what could be the structure which matches the spectrum. So, now let us see, when you say that there is, when we see that there is first of all you can see in this region, remember always the methyl peaks comes in this particular region, but in this what is happening, and remember there is one more, if you remember this we saw the general ranges of chemical shifts in the last class where we saw that if you have oxygen attached to a carbon and carbon attached to the hydrogen, and that hydrogen which is now will come downfield shifted because of the oxygen, and this typically means that this particular peak could be coming from an OCH kind of a moiety. So, we will write this down when we to derive the structure. So, basically we are having a kind of an OCH type of a moiety. Therefore, this hydrogen will come downfield shifted at around 4 ppm. And then we see this particular peak which is showing a singlet and it is 3. So, most likely this is an isolated CH3. That is why it is having 3 hydrogens and it is not coupled to anybody. So, that means it is not attached to any coupled to any protons. So, what that means is that most likely this is coupled now to a, this is attached to a carbon and this carbon does not have any hydrogens, because if it had an hydrogen in that case scenario it would have then got coupled to that hydrogen and this would not have been a singlet. The fact that this peak is a singlet means that it is attached to a CO, and therefore, this CH3 is not having any hydrogen to couple with. So, this is basically the way to interpret this particular peak which is showing a singlet, a tall peak, and it is having integration 3. So, 3 corresponds to 3 hydrogens. So, now we are looked at, we can see that there are two things now, there is this particular functional group and there is also a COHCH here which is shown on the right side. So, now remains the remaining 2 and 3, this 2 basically means there are 6 peaks. So, there are this hydrogen whatever with this, there are 2 hydrogens here. So, these 2 hydrogens coupled to 5 hydrogens, because only 5 will give you 5 plus 1 equal to 6 peaks. So, basically what this means is this particular hydrogen which is showing a sextet which is 1 to 6 peaks here, basically it means it is coupled to 5 hydrogens, only because if it is then it is coupled to 5 according to the 5 plus 1 rule, you will get, you expect 6 peaks. And then this one is a triplet. So, triplet. So, what this means, there are 3 hydrogens now which are coupled to this is basically 3 hydrogens means CH3 and it could be coupled to a CH2, and because of this 2 plus 1 equal to 3, triplet. So, what has happened is this particular CH3 what you see, so we will explain this in more detail. So, this particular CH3 peak, because there are 3 hydrogens, it is showing a integration value of 3 and it could be coupled to a CH2, I mean attached to a CH2, because of which there is a coupling between these two 3 and 2 between this methyl to this methylene, and because there are 2 hydrogens, this methyl will now show a triplet, and that is what you see a triplet here. And this sextet is coming because of a hydrogen which is coupled to 5 hydrogens, and we expect this kind of a moiety. So, if you put all these together, the structure which will satisfy this particular molecule is this shown here. So, you see we have a CH3, CH2, CH2, CO, CH3. So, basically there is a slight correction, this C is carbonyl. So, this C is attached to this oxygen, not to this oxygen. So, there is this got a shifted. So, basically it is a CH3, COO, CH2, CH2, CH3. So, what it basically it means that this CH3 is showing this singlet, this tall singlet here, this C double bond O, remember this has got shifted, this has to come here. C double bond O is an ester group, and because of the ester group this oxygen is attached to this carbon, and because of that this H2 gets downfield shifted. Okay. So, that this is the one which comes around here, and this you see there are 2 hydrogens in this, and therefore, the molecule which satisfy, now we have looked at the different peaks here, the molecule which will best satisfy all these conditions will be this. So, now let us look at how this can be interpreted. So, this is a CH3 peak which is an isolated peak which is not coupled to any hydrogens. So, that is why you expect a triplet here. So, this is what we looked at, and because it is attached to a carbonyl group, its value, the CH3 peak which typically comes between 0 to 2 comes at the downfield part, because remember if you look back at the slide where we looked at the chemical shift dependence on the carbonyl of the protons, because of this electronegative CO, this CH3 peak which normally should come somewhere between 0 to 2 comes at the edge of that, and it comes at a little bit downfield value. Now, if you proceed to this part, this oxygen is attached to this carbon, and therefore, this hydrogen is basically comes very much downfield shifted around 4 ppm, and because it is now coupled, this hydrogen is coupled to this particular 2 hydrogens, this will show a triplet, and that is why you see a triplet here, and the integration says that there are 2 hydrogens present here. Now, if you go to this hydrogen now, there are 3 hydrogen on one side and 2 on the other side. So, this hydrogen which are chemically equivalent, these 2 protons will expect 3 plus 2 plus 1, 6 peaks, that is sextet, and that is what is shown here, and that is what we said, that this particular peak is coming from a proton which is attached to coupled to 5 hydrogen, and you can see there is a coupling to 5 hydrogens here. Then finally, what we are left with is this methyl peak, which basically now is the peak which is showing here, this triplet here, and this is coupled to a CH2, and that is 2 protons, and that is what we saw here, that there is a CH3 which is coupled to 2 protons, and therefore, it is showing a triplet, and this is the triplet. So, this is how we basically find out the structure based on the NMR spectrum, that given the coupling pattern and integral, we can reduce the structure if the formula is, if this is given to us. So, let us look at the second example now. In this case we can again see there are 10 hydrogens. So, if you look at the integral, 6 plus 3 9, 9 plus 1 is 10. So, 10 hydrogens are matching with this particular formula. Now, let us analyze the chemical shift wise. So, you see there is a septate here, 7 peaks multiplied. So, if you remember Pascal's or n plus 1 rule, what it means is any the proton, the single proton which is having a septate basically means it is coupled to 6 hydrogens. Now, 6 hydrogens can be only possible if there are 2 methyl groups CH3 CH3. So, what it basically means is that we have a like this a spin system, this particular peak is coming probably because there is a CH which is 1 hydrogen coupled to 2 CH3s. So, only then 3 plus 3 6 plus 1 7, you expect 7 peaks for this. So, basically this is an isopropyl moiety. So, this is how we can interpret a given molecule. So, you can see that in basically if you have an isopropyl moiety, always remember you will expect to get 7 peaks, 7 J peaks, J coupling peaks because of this n plus 1 rule, 6 plus 1 is 7. So, this is what it could be in the molecule. If you look at this particular peak here, it shows 3, again remember 3 protons mean has to be CH3. So, there is a methyl group here and there is 6 here, means again 2 methyl groups, and these 2 methyl groups probably could be these 2 methyl groups. Okay. So, this 6 peaks together corresponds to these 2 peaks. This isolated methyl is not coupled to any hydrogen and therefore, it is a singlet. So, again remember according to the previous slide we saw that this probably comes from something like this one, this particular peak could be an isolated CH3 which is now having no hydrogen as coupling. So, it could be SCO. Okay. So, therefore, this CH3 is an isolated case, isolated hydrogen methyl group, and therefore, it does not show any coupling. So, now we can now add up all this together and come up with a probable structure, and looking one more where we can see is that this hydrogen he is now coming at 5 ppm, which means this hydrogen probably there is an oxygen here. Only if there is an oxygen here, only then can this hydrogen become so much downfield. So, therefore, there is an oxygen here and there is a carbonyl here. So, if you add these together, what happens? This is the structure. So, this is the structure of the compound which we corresponds to this formula. So, if you see there are 5 carbons here, 10 hydrogens here and 2 oxygen groups according to this. So, if you had a IR spectrum with you, IR spectrum would also give an indication of an ester group because of the vibrational frequencies of ester. But if we have a carbon spectrum also will be very useful here, but right now we are, as we said, we are relying only on the hydrogen. When we include the carbon spectrum later on, you will see that it becomes more easier to interpret, because a carbonyl frequency in NMR for a ester group is much different from what you get from a ketone group or what you expect from an aldehyde. So, based on the carbonyl peak also you can figure out whether the ester group is present or it could is a carboxylate group and so on. So, this is one second example where we see that given a molecular formula and the spectrum, we should be able to deduce the possible structure of the molecule. So, let us go to the next example. So, the previous 2 slides, previous 2 examples were actually structural isomers. So, they were isomers of each other. So, in this case now we have a halogen compound. So, now let us look at this molecular spectrum here. So, here what do we see? We see a triplet and a quintet. So, these are 5 peaks here. So, you can see 1 is to 4 is to 6 is to 4 is to 1 roughly in that particular ratio, and the area, if you take the area under the peak, what it says is that this should be 2 corresponding to 2 hydrogens and this is corresponding to 4 hydrogens. So, if you add these 2, 4 plus 2, you basically get this 6 hydrogens, which is satisfying this particular formula. So, now let us see what happens. So, if you have, again remember, if you have a bromine attached to a hydrogen, because of the shielding, that because of the inductive effect, this hydrogen, any hydrogen attached to a carbon which is attached to a bromine will be downfield shifted. So, if you recollect again the slide where we saw the general ranges of chemical shift values, we see that if CCl, CBr or Ci, a halogen compound typically comes somewhere between 3 to 4 ppm for that proton which is attached to that carbon. So, that probably what is happening here, that there is a hydrogen which is attached to a carbon and which is attached to a bromine. So, basically what it means is that this particular peak is probably coming from S proton which is attached to a bromine, this hydrogen. So, now we have 4 hydrogens like this. So, 4 hydrogens basically what it means, that we have basically a CH2Br, this whole thing 2 times. Okay. So, if you have that type of a system, then we would expect 4 peaks. So, we would expect 4, because 2 into 2 is 4, and therefore, this and Br, there are 2 Br is coming twice here also in the molecular formula. So, therefore, it could be that this Br is they are repeated 2 times, and the CH2, this whole moiety is repeated 2 times. So, that is why we are getting this 4 peaks, but then there is a triplet here, this is triplet. So, what it means is this CH2 has to be coupled to another 2 hydrogens, this hydrogen, only then you expect according to the n+1 rule that this will be a triplet. So, that means what we expect in this molecule is that this whole unit is coupled to a CH2, and if that is so, then that CH2 could be this, because there are 2 hydrogens, and therefore, the CH2 which is coupled to this 4 hydrogens could be that, but then it has to have a quintet. A quintet means 4 coupling, 4 protons, because 4 plus 1 is 5 and 5 is a quintet. So, that means the CH2 which we are looking for, which is coupled to this hydrogen, has to be now in between these 2, because only then on either side it will have 2 hydrogens, and therefore, it will give a 5. So, let us look at the structure which is shown here. So, this is what the structure is, that this is CH2Br, and this unit is appearing 2 times here also and here also. So, that is what is shown, that is what I mentioned here into 2, and in the middle center there is a CH2 group, and that CH2 group is this peak. How do we find out? We can say, look at this, it is coupled to this hydrogen on one side, and these 2 is coupled to this hydrogen on another side. So, 2 and 2 4, 4 plus 1 rule, n+1 rule gives 5, and 5 is what we see here. So, that corresponds to 2, and the integral also says there are 2 hydrogens, which is 2 here. Now, we are coming to here, these 2 and these 2 are equivalent, because there is a symmetry. If you draw a line here, an axis of symmetry which separates these 2, that means these 2 are equivalent. So, this CH2 is same as this CH2. So, therefore, you expect same peak for this, both this hydrogen and this hydrogen, and 2 plus 2 is 4, and therefore, the integral is 4. As far as J coupling is concerned, both of these hydrogens are coupled to this center hydrogen, 2 hydrogens. So, therefore, both of these will show a triplet, because they are coupled to each of them is coupled to this hydrogen, these 2 hydrogens. So, therefore, there is a triplet, and that is what you see here, you get a triplet from the edges. So, we can see this is how we can interpret the presence of the coupling based on the coupling and the integration. So, we will look at the next example, which is here. Now, there is a very interesting situation here. What is happening is, look at this case, this is CyH12O2, but here there are 12 hydrogens, but here we see only 1 and 1. So, if you add them up, it is only 2 hydrogens. So, how can that be? So, remember, that is why it is very important, the word what is written here is relative integrals. Relative integrals means it is relative to each other, they are equal. It does not tell you the number of hydrogens. So, that is the biggest one of the not biggest, I would say, drawback in NMR is that it gives always relative to each other. So, if I take this as a reference, I mean in terms of the height of the peak, this height is same, area is same. So, I would say this is equal, but it does not tell me the absolute number of protons. So, there is a big issue. Only if I had another reference here, let us say TMS, which has 12 hydrogens. So, if TMS peak, if I know that it corresponds to some x hydrogens, relative to that, this could have given me a more correct picture, but that is what we do not have. So, now what we have to look at is how do we interpret this particular case. So, we can see there are 12 hydrogens. So, it could be that there are 6 hydrogens here In this, under this peak corresponds to 6 hydrogens, and this peak also corresponds to 6 hydrogens. So, if that is so, then it will match with our formula that 6 and 6 together is 12 hydrogens, and both are 1:1, means they are equal 6 and 6, and therefore, that adds up to 12. So, that is the most likely the scenario, because we are only getting 2. So, you can't expect 2 hydrogens. This is 6, this whole peak corresponds to 6 protons, and this whole peak corresponds to 6 protons. So, now if there are 6 protons, 6 here, how can 6 protons come under one peak? It automatically means there are 2 CH3 groups, 2 methyl groups, they corresponds to one particular peak here, and there are another 2 methyl groups corresponding to this. So, that is how we have to interpret, because there are 6 hydrogens. If I take here 6 hydrogen has to come from 2 protons. Similarly, 6 hydrogens here, sorry, 2 methyls. Similarly, 6 hydrogen here has to come from 2 methyls. Now, there are 2 oxygens remaining here. So, how do we interpret that 2 oxygen? So, what it basically means, now look at this value, it is somewhat downfield shifted. So, if this is a methyl peak, remember methyl peak we said it always comes between 0 to 2 if it is not attached, the carbon of the methyl is not attached to any oxygen. But if the carbon of the methyl is attached to an oxygen, then it is comes here, that is called a methoxy. So, a methoxy group is like this, a methoxy group is OCH3, this is methoxy. So, only if there is a methoxy group can that methyl come at downfield shifted, and that is what we are seeing. We are saying this is basically coming from a methoxy group. So, that means there are 2 methoxy groups in my sample, because 2 methoxy groups will correspond to 6 hydrogens, and that is what is coming from here. That means the remaining 2 are only CH3, because the oxygens, if I put 2, then it is already taking care of this oxygen. So, therefore, putting all this together, this is the structure which is most likely matching with this particular spectrum. So, you can see there are 2 methoxy groups here, there are 2 methoxy, and there are 2 isolated methyl groups, and this methyl is not coupled to this methyl because protons, because they are very far away, okay. And similarly, this methyl is also equally far away. So, this is a very symmetrical structure, and because of the symmetry in the structure, these two are equivalent, these 2 methyls, and they together corresponds to this peak. And this OCH3 methoxy groups OCH3, they are again 6 protons, and they correspond to this peak, and this is called a quaternary carbon, and it does not have any hydrogens. So, therefore, you do not see any peak in the proton. But if you go to carbon spectrum, in a carbon you may be able to see a peak for this, but remember that we are not looking at right now, we are only trying to get the structure based on hydrogen. So, this is how we can interpret the hydrogen spectrum based on this. So, we look at the next example, which is now this particular molecule. Now, here it seems we are looking at the integral, if you see, and the spectrum, it seems to add up properly. So, there is 9 plus 2, 9 plus 1, 10, 12 and 14. So, this seems to be fine, matching well with this one. Now, let us see, there are different, how many types of hydrogens are present, 1, 2, 3, 4 and 5. So, there are 5 types of hydrogens in this molecule, and this molecule seems to be now having 5 hydrogens. Now, if you look at this particular start from here, there is this doublet, is integral is 6, relative integral is 6, and if you look at this, there is one hydrogen which is a septet. So, this we encountered in the some example a few slides back, where we saw a septet there. So, remember the septet we said is isopropyl group. So, what basically is this septet? This septet is coming from isopropyl group. Only then this will give a septet. So, this most likely is this particular peak which is showing to 1 proton. Similarly, these two could be most likely this, because 2 CH3s are now each of these CH3, what we are seeing can be giving will give a doublet. So, if you see each of these CH3 is coupled to this hydrogen, and therefore, this 3H3 will be a doublet, what we are seeing here, this doublet, and this septet is coming from this hydrogen. Now, if you look at CH3 and remaining this 3 and 2, and again remember there is a downfield shifted proton and corresponding to 2, which means it is most likely attached to an oxygen directly. So, O CH kind of a moiety, and OCH we saw earlier can come from the ester group which is having like this. So, basically it is OCH and there could be a CH2, something like this. So, here this CH comes at a downfield shifted because of the oxygen attached to this particular group. Okay. So, this is basically this particular peak where there are 2 hydrogens. So, I have written only one here, but there is 2 and it continues further. So, if you put all these together, this is the structure possible for this particular molecule, because you can see here that we have now CH3 that is and this CH isopropyl group, and therefore, this hydrogen where the arrow is here, that is giving this septet, and that is 1 proton, and these 2 CH3s are the 2 doublets which we saw here earlier. So, this is matches with that particular case. So, remember always a septet if you see in your spectrum, it automatically means an isopropyl group is most likely present. Of course, this is not the final confirmation, one has to first build a structure and then figure out, but most likely 90% of the time it could be because of this particular moiety, and therefore, you are getting a septet. But if you expect this moiety, then you should also expect a doublet which is here, like a proton which is of intensity 6. Then you have the CH2 which is attached to oxygen, and because of this CH2 comes downfield, and because this CH2 this hydrogen is coupled only to one this hydrogen, and therefore, it is having a the doublet. Okay. Now, we will go to this particular case, here CH2 CH3, here this CH3 is showing a triplet and this CH2 is showing a quartet. So, in this manner we can see that there are 7 hydrogens now, 1 2 3 4 5 6 7, and there are basically 2 oxygens and there are 14 protons. Okay. So, in this way we can interpret this molecular structure. We will further take it up in the next class, more complicated molecular structures. We will continue this. So, we have looked at 5 examples, we will see 5 more examples, and then we can actually get an idea of how this proton spectrum is analyzed in absence of other data such as carbon spectrum or mass spectrum or IR spectrum.